Good afternoon, everyone. Uh, so, my name you can see there, Manish Srivastava, I'm faculty in EE, and uh, so I guess I'll take the first half an hour, 40 minutes to kind of go over the logistics. Just looking at the head count out here, so obviously a lot of you are not enrolled in the class because I handed out, I think, 34 or 30, 35 PTEs. So I want to talk about how that will work. Unfortunately, though, as I've explained in my email, I'll have to disappoint most of you, but let's talk about that. So, uh, information about me. I work in embedded systems and kind of related areas. My lab is called Networked Embedded Systems Lab, and I belong to both CS and what's now the ECE department. Um, uh, my lab, those of you take the corner, southwest corner of Bolter Hall, the elevator is kind of right opposite that. So oftentimes I'll do office hours and stuff like that there. But many of you during the course of your projects will get to use, will need to use resources in that lab as well as perhaps interact with some of my students. So, um, so anyway, so that's the location. Office hours, as of now, I plan to have them one on Wednesday, kind of after the class, 4:30 to 5:30, and one on Friday. But I'll periodically juggle them around a little bit, and also I'll see if sort of this slot doesn't work out to be convenient, so we'll adjust that. Um, let's see what else. Hopefully you are on Piazza, or at least if you're enrolled, you should have received invitation on Piazza. Generally speaking, I would really prefer that you pose your questions on Piazza. I have the anonymous posting enabled, so you could not only be anonymous to your peers but also to me in case you want to comment on any aspect. Um, uh, but if you choose to email me, then please put the course number in the subject line so that um, it doesn't get filtered away. My assistant's information is there, but you probably won't need to interact with her or anything. Um, the course itself, hopefully, most of you at least have some sense of what embedded systems are. But generally speaking, these are systems that end up interacting with physical worlds and physical world and things in the physical world, humans and other things in some shape and form. Uh, if you were in the EC seminar just before the class, then that's the Professor Sesha kind of went over some interesting examples of that and kind of issues that exist. There are a whole bunch of other courses that exist in this space at UCLA. Unfortunately, as most of you have discovered, mine is the only course being offered this quarter, partly because Professor Bill Kaiser is on leave and Professor Ankur Mehta, who teaches the robotics sequence, he's busy teaching undergrad class this year. I will be teaching a new course in winter under 209 AS, and that will focus on IoT security. Normally, I teach a course which focuses 202B, which focuses on energy-aware embedded systems. So there's a whole bunch of these courses. Some of them you'll therefore get to see next academic year. Generally speaking, sort of the term embedded system is, I guess, arguably a bit uh, old-fashioned in a way, in the sense that it's been superseded by newer jargon in terms which keep emerging, and there are a couple which are in vogue in recent years. One is called cyber physical systems, and I guess a variant of that, human cyber physical systems, which today's speaker in a way talked about, and also Internet of Things, and there are other terms like swarm and stuff like that. So there are a whole bunch of other generally equivalent terms that are floating around. But basically, you can think of these things as either special cases of kind of the broader embedded system term. So IoT um, particularly refer to things being connected over the internet or using at least internet type technologies, and cyber physical system bring out the element very strongly that there is some sort of a coupling with the strong coupling with the physical world, and swan basically refers to a whole bunch of these things out there, again perhaps very similar to IoT. So the other thing which has been kind of driving this is a whole bunch of computing technologies, sensors, wireless, these kind of things, which are coming together under this umbrella. So there are strong intersections with a bunch of other disciplines in terms of wireless sensor networks or wireless sensor and actuator networks. Used to be a term which was pretty fashionable, let's say in the early 2000s. Um, so there are other similar sort of things that you would hear about. What are embedded systems? So very, I guess there is a broad set of characteristics that embedded systems share, and so firstly, these are these are computers which are oftentimes dedicated to some specific function. So as opposed to our laptops and all, which are really meant for general purpose computing, so a whole wide variety of things. Embedded systems usually are being embedded inside some particular system, let's say a car or something. They are really designed for a narrower set of functionality. Oftentimes, they run applications which are aware of their physical world existence, so their location, timing constraints, things like that, and obviously interaction with the physical world and increasingly kind of humans and all are an important part of that. By comparison, laptops and all these kind of things are really intended to be one where a wide array of things could be run. Now, this boundary often gets blurred. So, smartphones, for example, are increasingly becoming very general purpose. Okay, even though they kind of started out as embedded, or even things like, I don't know, take your drones for example. There are app stores for drones. Okay, so it wasn't like that. So there's obviously always a trend towards things which are embedded. We're trying to make them more flexible, more at least more friendly to third-party software as well. So boundary is sort of blurred, but nevertheless, it's fair to say that things like a data center or a server or a PC were designed for not a particular single purpose as mine, but rather to support a broad array of computing needs. Um, these things are obviously kind of all around us, and if you just sort of bother to count the number of distinct devices you end up interacting with, which have some sort of computational capability in them that's ever increasing. Okay, I mean, just the car you um, uh, drive or whatever vehicle probably has a few hundred processors, and that's just the start of it, just around your home devices and all. So it's sort of quite pervasive. These systems are quite pervasive, and again, a lot of things that you make use of, the electrical grid, meters in your home, perhaps increasingly some of the smart lighting, these kind of things. They're all examples of embedded systems. IoT is kind of a term which came more later, and essentially it arose out of the fact that people started to connect devices of various types onto the network. Early days, it were kind of just fun stuff like people putting their coffee maker in the lab onto the internet and things like that. But gradually, we've gotten used to the idea that lots of things are now on the internet, accessible in some shape and form. Um, Even sort of large scale systems, power plants, these kind of things are all your traffic light systems, whole bunch of stuff. Our cars increasingly are, and so on and so forth. Um, and it's probably at this stage fair to say that the number of the bulk of the devices which are sitting on the internet are really not your traditional computers, but it's these kind of new devices. Oftentimes, they may not have public IP addresses. They may be hidden behind sort of various NAT type technologies, so that you don't get to interact with them directly, but they are kind of out, they are kind of out there. Um, just at my home, I have close to a couple of hundred IP addresses of different type. My home is perhaps an extreme example, but by the time you start counting things, televisions, your net, whatever, your Apple TV or Roku box, and a whole bunch of things, they all are sort of sitting on the network in some shape and form. Uh, Very broadly, what so currently when you look at the IoT devices, I think most of them fall into the category that they probably have some sort of a sensor. They're grabbing some sort of sensor data and pushing it out either to your phone or to some sort of a service. But more generally, and as particularly as technology advances more and more, they kind of go through the whole loop of what an embedded system device typically looks like, which is namely there's a sensing component, there is some sort of an intelligence component which makes inferences from this data, perhaps comes up with some decision and all, and then perhaps some sort of an action component. And we do see these already in some cases, so like smart locks at home, they are an example where there is an actuation component, or control of AC at your home, or some newer homes have um, window shades and all which are controllable. So the control element is increasingly becoming much more prevalent, although still fair to say that vast majority of things that we see around us are still very sensing dominated with Fitbits and so hopefully, so in the course we really kind of take a look at the whole path. The other, I think, the big change which is happening is the type of processing that you are doing, that devices are doing, is changed substantively. So, sort of those of you, vast majority of you are the E side of things. So we kind of grow up learning about signal processing and detection estimation theory and these kind of things, and make essentially sort of do some signal processing on sensor data, derive some simple event, and do something based upon that. Big shift which is happening sort of in recent years is that all that stack is being thrown away in favor of techniques which have emerged from machine learning side of things, essentially more of a data-driven approach. So as opposed to, if you may, trying to draw some insight about the structure of the signal and kind of working from that to sort of just general purpose data-driven models, machine learning algorithms kind of coming into play. So in essence, I guess very loosely speaking, technologies that fall under AI are kind of the key part of it. In many ways, uh, that is not unusual because robotics was always like that. And in that sense, you can say that what we are seeing happening at a larger scale are robots of different types, namely at different scales. We are seeing capability using sensors to perceive the world, using AI type methods to sort of do some cognition and decision making, and then finally using some sort of actuators to affect the state of the world. And that, in a nutshell, what all of these systems are really kind of seeking to do. Um, a whole bunch of other challenges that have begun to emerge, which are more a nature of the degree to which these technologies have penetrated our world, and also the consequences. So again, today's seminar kind of the discussion about like humans play a big role, securities, privacy, all these kind of concerns which um, when these systems were less prevalent were not as important. We begin to see them. CPS is a closely related term, and I guess you could say IoT is a type of CPS, but not all CPS are IoT. So CPS is a term which got popularized more by National Science Foundation and a bunch of researchers who were looking for a cute name to attract some more funding. But at this stage, it has caught on reasonably well, and it does describe a corner of system. So essentially, the notion out here is I have computing systems which are interacting with the physical world, but they don't need to be just IoT. I mean, your airplane is an example of a cyber physical system. Your power plant, your traffic system in a city. So they may not be IoT, but they share the characteristic that there's computation in conjunction with physical world and perhaps in conjunction with human agents. And the main point which the community, CPS community sort of brings out is that to reason about the correctness of the system, you cannot simply focus on the computing part as you might in a general purpose setting. Okay, like let's say you were trying to decide whether your compiler works correctly or Word works correctly. You just have to focus on the software. On the other hand, in these systems, correctness of the software requires you to also model the entities, the environment it is interacting with, and then reason about the properties of both, the whole collective. And that raises the issue that you got to model the other side also. You got to model the physical world, laws of physics. You got to model humans. If you're designing a system, let's say a medical system, operators fail. Humans have sort of complex behaviors, and oftentimes the way, for example, you might model the physical world might be in the more continuous domain, and your program you might reason as state machine or some automatic. So the complexity often comes from that you have very different worlds which are coming together, and now you need to reason about them. So that was one big sort of selling point behind CPS, that these are computing systems whose safety and correctness and all these other properties that you want can only be understood if you model the whole system. Um, um, so yeah, so that's what CPS is, and I think what's happening, uh, sort of a further development which began to happen is that it's not simply CPS, but it's really human cyber physical systems. So while you could say humans are also physical, so what's the big deal? I guess the only sort of issue is that the way we model physical systems is of relatively well understood in the sense that physics and mechanical engineering and civil engineering and all can provide us insights into how a bridge might behave or how a car works or how a drone works. But when it comes to humans, the state of science is much less advanced. So while there is certainly some insights from medicine about how our physiological systems work, but when it comes to things like behaviors and all, we are still in very, very early stages because the social sciences, um, psychology, and all are far less on a far less mathematical footing for us to sort of work with this. So I think a lot of complexity is coming, that our inability to model complex human behaviors, what will be the impact of a certain action on a human. But we face them because humans, at the very least, are operators on these systems. There's a slide I stole from a talk by today's speaker. Um, but in many, many cases, I mean, you have drivers in cars, you have pilots in planes, and sort of people, self-driving car may encounter a car which is other cars which are driven by humans. So it's sort of a complex interplay of humans with CPS that's happening. Buildings are like that, medical systems are for sure, transportation. These are all examples where humans exist, and not just necessarily as operators. So if you kind of think about, we as humans play multiplicity of roles in these systems. We are often sensors. For example, um, it's very common in many settings where um, in medical context, for example, there's a concept called ecological momentary assessment, which is essentially a fancy term for a questionnaire. The system asks you, how are you feeling? What's the pain? Is your pain on a scale of 1 to 10, how it is? The kind of things that your doctors ask, okay? And so that's an example of human as the sensor, because we perhaps don't know how to sense those things. Human as an actuator. In many cases, human replaces the actuator. Can you think of some example of that, David? Human as an actuator.
Driver assistance, you hear a beep, you have to turn around.
Okay, take control of your car, right? So the system beeps. Any other? phone says, "Go drink water. You're getting dehydrated," right? I mean, so you are the one because again, there are places where actuation is sufficiently complicated that it will kind of perhaps remain a bit like that. Human as a decision maker, that is, human replaces the control system, or at the very least, maybe human control coexist with some sort of autonomous control. A couple of ways it can happen. Again, I think today's talk brought some of that out. That is, it could be that human driver and that autopilot kind of stuff coexist, and then the car has to somehow fuse those. Much more common is the situation where human is the outer loop, kind of some sort of a slower decision-making loop, and so that could be a doctor, for example, and then the faster local loop is some sort of autonomous loop. So there are different ways human can enter into decision-making and kind of control kind of things. In complicated military scenarios, again, you probably don't want a drone to make the decision to autonomously fire off a missile. If nothing else, for legal and optics of the decision making. So again, some sort of a commander or remote pilot would always be in the loop there, and kind of at the very least giving go no go kind of a decision there. So anyway, those are some of the things that I hope to combination of lectures and presentations that, as you'll see, you guys will have to make. We'll go through that. And yeah, the slides are on Piazza. I can read through it, but kind of the main point is there's no hard prerequisite that I require in terms of courses for this class, simply because it sort of draws upon many disciplines. But roughly speaking, my expectation is that number one, you should be good at some of the core skills, particularly programming. Okay, so if you're uncomfortable with programming, this course is not for you, because very broadly, I'm expecting that you have training equivalent to what a good computer engineering undergraduate program would have. So that's where I target this course. If you are missing those things, then you'll have to pick up on your own, but oftentimes it can be hard. So I know many of you come from just circuits background and want to take this course. If you're uncomfortable with software, uncomfortable with sort of bare metal type programming, those kind of things, then you'll probably you should rethink and maybe build up your skill set in that direction. Um, Course registration issues. So I handed out 35 PTEs, and as you'll see shortly, the reason, uh, a couple of reasons why I cannot scale this course arbitrarily. Number one, there's an element of this course where I have you guys present, and that means it's time away from lecture. So I cannot just increase the class size arbitrarily. Second thing is a project, and we also actually hand out hardware for the homework assignments. Again, these are things which I bear out of one of my research grants. University doesn't support these, so I cannot again ad infinitum kind of incur the cost. But that apart, again, grading these things and all requires significant manual effort by my PhD students, again, unpaid for. So again, I cannot just scale these things, unfortunately. So it's not a lecture theory where infinite scaling as long as there are readers and TAs. So bottom line, I plan to stick to the head count. I handed out a few more than what my target was, which is 30 students, but I handed out 35. So at this stage, only if the head count drops below 30 would I hand out additional PTEs. Now, having said that, it always happens. I think by the time, once you look at the grading schema and all, you might decide that this course is not one you want to engage in. Um, in any case, the other thing is I had asked people to fill out the web form. If you didn't fill out the web form, then there is no shot at the PTE. Okay, so that form is over. But if you did and the head count drops below, I have sort of a few other names selected, and I'll just hand out based upon that. Um, and the other requirement is attendance during this. Like you can't just show up towards the close of the enrollment and expect me to take you. There was a whole bunch of factors that I kind of took into account. So firstly, the very nature of embedded systems is that it really straddles computer science, CES, and signals and systems. Okay, and in fact, even parts of mechanical engineering. So I want a well balanced body of students, which meant that I couldn't simply just go by you're a second year CES student, irrespective of background, and just hand it out. Okay. The other thing is students who were actively engaged in research in groups, they got the priority simply because they need it and they're making a long-term investment in this area. So these factors were kind of a balance of things. I did go through your prior experience and things like that. All things being equal, other things being equal, I did prioritize second year students over first year students, PhD over masters, and so on and so forth. But in any case, that's I sort of just handed that out. If you are shopping and you got a PTE and you are doubtful or you decide to drop out, please make the decision early so that I can free up because your peers who are waiting. I mean, it's hard to attend multiple classes um, for a long time. The other thing is, if you do drop out, don't just silently disappear and say, okay, close to whatever at midnight of the last day you will remove because I have no way of knowing. So please sort of de-enroll from the course on the registrar website because that's the only indication that I would have. Okay, so that's there. Um, Course components. So there are going to be some homeworks, 25% towards that. These homeworks will have a programming component. And one thing I've been trying the past couple of offerings of this course is kind of an auto grading system where essentially, as you might imagine, kind of testing whether your program running on a piece of hardware is correct or not is really, really awful. And the only way it used to work was that we would waste a couple of days, my students would, and then sort of students in class would come and they'll plug their stuff to the oscilloscope and all and kind of we'll measure, aha, the waveform looks good, not doesn't look good, very time consuming. That apart, inconsistency because one of my students may interpret the same thing differently than another. So what we have done is there's a server set up in my lab and which has exactly the same kind which essentially has kind of ability to generate waveforms and capture waveforms and then analyze it against the specification that the homework has. So we've been trying that out. There are growing pains in that, I don't deny it, and also unexpected usages, students hogging the server for long periods of time, and also as we've been learning, sort of we've been refining that system. We use that, but you have to still bear with us. I think the nice thing is that you get feedback which is more consistent. Everyone has been graded on same metrics. And the other thing is you actually get multiple shots of it. You don't have to wait until the grading time to discover something is wrong. You can kind of refine it. So anyway, that's homework, 25% of course. Presentation. So kind of the idea out here is that either individually or in pairs, starting a couple of weeks from now, we'll basically start having this, that part of the lecture would be a presentation. Or I, depending on how things go, or I may have kind of a day set aside every 2-3 weeks where the entire lecture is just a bunch of presentations. And the idea is that we either pick up, I expect you to, I'll assign either a sort of paper which describes something interesting or some new technology that has emerged relevant to this and you make a presentation on it. So typically individually or groups of two, more commonly groups of two. If it is a technology and all, I also expect you to kind of dig into it and then do a show and tell, okay? Because otherwise, I don't want you to go up and read a data sheet because that anyone can. So the idea is that just explore things a little bit. If it's a research paper, then you kind of essentially end up critiquing, examining it, and more of that. So that's 20% of the course. And then finally, project, which is 55%. And the idea out here is, so the kind of project which is not acceptable is a literature review. So that's not the intent. I want you to get your hands dirty. So literature review in some senses is kind of happening out here to some extent. So the nature of the project has to be either you are analyzing something or designing something or experimenting, collecting a new type of data set, something of that nature. There has to be some component like that. There's a report, there's a presentation, and depending upon the project, possibly a demonstration also. Okay, so there are I'll talk about how sort of the project grade in itself is split, but the idea is that the project is how you kind of get to dive into something. I typically, what happens is this phase I work with my students and others in my lab to kind of come up with a set of project ideas, and I'll throw them out, but you are not limited to them by any means. There are some constraints I'm going to describe that I would present. Um but generally speaking, the idea is this is a project that you need to define. I will, the number of people engaged in the project has to be commensurate with the difficulty of the project. Um, Again, remember it's a quarter system. By the time you're settled with the project and all, 3 4 weeks will pass. So really, you have around 6 weeks or so typically to do a project. So keep that in mind. The sooner you work out the details, because many of these projects may require to purchase items, then that takes time also. What happens is usually you give the list and I have my assistant sort of finish the order. But if you decide on those parts much later, then you can't really help. Okay, and of course you need my approval, and oftentimes things that are needed I may already have in my lab. But anyway, I think you need to approach this thing in a more kind of a systematic manner. Oftentimes, these projects then themselves lead to MS projects, MS theses, and some rare cases, even PhDs, papers, and stuff like that. So there are always a few sort of projects which stick out, but that's not certainly sort of going to insist by any means. Okay. Um, Project timeline. So by October 18th, I want the project topic, abstract, team finalized. That means prior to that, you have met me and discussed and stuff like that. Okay, so or with the kind of the students and all who are mentors for the project. By October 23rd, I want the creation of a project website. So the way I'm thinking of doing it this time, so historically what has happened is I let the students create the project website. The problem then happens is they often create it in transient places, and then a few months later I discover that website has disappeared, and along with it, kind of a rich record of what happened. So this year, once the project group is finalized, in my GitHub account, I'm going to create GitHub repositories for every project, and then I'll make you contributor to that so that you take it over, but it's hosted under my labs account. And GitHub, how many of you have used GitHub or use it regularly? Fair number. Okay. Those of you not, it's a great thing to learn. But GitHub also allows each project to have a web page, okay, using the Markdown language for marking. Well, kind of a specialized way of writing web pages. So I would like you to have that. Your project report is nothing but the contents of that website covering certain essential things, and then any code, data, stuff like that is also has to be there. The only situation under which this will not work is that if you decide to pick up projects which for some reason you want to keep private, um, in which case we can discuss, we can make it into a private repository and kind of work around it. It happens very, very rarely. Um, Another thing which comes up is some of you are in research groups. I will not approve out of keeping the field even for everyone. I will not approve projects which relate to your ongoing research in your group, just because it is not fair, and I don't want to deal with kind of those kind of issues. So, for example, if you are in, just to pick one name, Professor Bill Kaiser's group, there's a lot of work on wireless health. I would say stay away from that. Pick something different. Learn about something else. Likewise, if you're my student, same story. In your case, I would know what you work for research with me, so obviously I will not approve it. But the idea is you have to go beyond, okay? And just I think it's also just fair to your classmates who are not in any group. So that would be one constraint that exists. Um, but again, if there is something that relates broadly to but is very distinct, we can discuss. I'll probably need to discuss with your research advisor just to make sure that it's sufficiently distinct and not kind of the intent is no double dipping and no unusual advantage just because you already are doing research. Let's see. Um, there's a midterm report on November 20. including preliminary results, code, stuff like that. Then during various days of during the finals week, I would basically schedule project presentation and demonstrations. What I do is I kind of set announce a set of slots. You sort of sign up for them. Um, some of you, I realize, just before Christmas break, you want to leave early. We can schedule something during the finals week also if the project is in that state. Another one which I'm usually okay with if you want to do a recorded presentation, that's fine as well. So I'm sort of fairly flexible, and frankly, around that time there is a whole bunch of other things going on both in your lives and mine. So it's possible that find none of the slots I hand out work for you, or and so we can kind of discuss those kind of um, by Friday, December 15th, this is the last day of this final report. Essentially, the website should have the right type of content to finalize, slides, as well as all the ancillary information. Okay, has to be there. And so any changes subsequent to that date would essentially be ignored. Now, one other thing which often happens is, which is the very nature of these projects, that things didn't quite work out the way you wanted, or maybe there was some particular part which got delayed, or something along those lines. Then we can discuss, and I am always open to the idea of then you taking an incomplete grade and then finishing it off in the subsequent quarter. But I will not do it if your performance during the project during the quarter was simply you just slacked off. Okay, so kind of the idea is something beyond your control kind of delayed things. Okay, or maybe you have reached a point where just some additional effort and then it would really make a big impact on the project. But it's not meant to again to emphasize that this quarter was heavily loaded. Let me just sort of defer everything. So that's not going to work. The other thing is if you have doubts about doing being able to sustain through this course, then do not pick up a group project because UCLA, for those of you new, will discover lets you drop the class until in our case it would be Friday, December 8th until I guess close of business time, which is ridiculous, but they do. But what happens is if you drop, then your partners are kind of left holding the bag because they don't know how to do it. So if you have doubts, then don't either don't take the course or better yet. So that would be the preferred thing. Don't take the course, but if you do and then decide something just forces you to drop, then at least don't do a group project because then it just hurts your partners. Uh, from my side, the fact that your partner dropped out is I can't really deal with that. Okay, so you'll just have to plan for it. Maybe as you form teams, get that commitment. Okay, I mean I think you have to be the judge of the characters. Okay, because it's a no-win thing from my side. Okay, so that's that would be my stance. Any questions on? Okay. Yeah.
How are you going to divide the grades?
Well, so firstly, the high level one we already saw, right? 25. 25, 20, and 55. Okay, and now I'll talk about how I will divide things within the project. Okay, so project proposal 10%, 10% of the project rate. Okay, midterm report 15%. So as you can see, roughly a quarter of your report actually depends upon what. Quality of work and effort 25%, and this is the place where I want to emphasize that um, I encourage you to take things which have perhaps more uncertainty or difficulty, and you try your best, then pick something extremely simple. Okay, so this is how I normalize for it, right? I mean, if someone took an ambitious project, maybe decided on an approach, but it didn't yield positive results, that's fine. That's research. At that stage, while I cannot judge you on the basis of how accurate your output is or whatnot, but I can certainly assess you in the manner in which you approach the problem and different approaches and how much effort that you put, which I get to know through by you interacting with me or interacting with project mentors for these projects. Oral presentation and demonstration, 20%. There are always a few groups who end up taking this thing very slack fashion. So it's very important that you approach this thing as you might any formal presentation, which means make slides, if there's a demonstration, maybe do it. If the demonstration is not possible in a live manner, maybe do it offline, capture a video and show that. So there's a variety of different ways, but that's really important. Final project report, that's important. One other thing I would emphasize is, unfortunately, I think a lot of research, even let alone class projects in CS and EE suffer from it, which is one result from one experiment on some unspecified condition doesn't say anything about your system. Okay, for your results to be statistically meaningful, they have to be supported by multiple independent experiments, hopefully over a range of conditions that are relevant. Ideally, you should present some sort of a confidence bar associated with your results. So kind of things that make for good science. I think that's extremely important. So let's say you are inferring, I don't know, for the sake of example, let's say you're designing a system which using sensors is going to infer what my activity state is. Okay, just doing it once, okay, doesn't really reveal anything. Other issues, just repeating it for the particular person probably is not very sensible in this case. You should try it out on other individuals. So the degree to which you do a fair comparison, a statistically valid comparison, and a comparison which makes sense, I think those things are going to be extremely important as I evaluate the quality of your work. Finally, I set aside another 10% for interaction and updates during the quarter, which means I don't want you to write the proposal and next time I get to see any progress is a midterm thing. Okay, so continually along the way, interact with me or interact again with the project mentor. So roughly a third of your grade really kind of is dependent upon this upfront work, and this is a third of 55%, so that's roughly 20% of the course grade. So I do want you to take it seriously, not wait until 8th or 9th week to start doing the project, because then you are not going to get anywhere on that. Any questions?
Do you have any example projects, ideas?
Yes, actually, so next few slides, I'm not going to go over those, but I have a list of things, including from the most recent one URLs as well. Okay, so if you download this thing from Piazza, you can kind of just work off that. More project guidelines, kind of essentially these are sensible engineering guidelines. I'll let you read on your own. But again, kind of the idea is that in most cases the intent is not to repeat things, go around looking for things which exist and leverage them in your project. I don't want these projects to be exercises in replicating something that someone has already done. I would rather that you introduce some new delta, but you must acknowledge, very important, so that you don't fall into plagiarism kind of situation. Acknowledge anything that you are using, okay, from other sources. You can work into up to groups of 3, but generally speaking, I think the best things work out in groups of 2. But some projects may need groups of 3. Anything beyond that has to be a particularly integrative, elaborate project. And I would like the project report as well as when you make your presentation to describe what each one of the team member did. Okay. Hopefully the contribution is roughly equivalent. If it is not, I will take that into account in grading. Okay. So, but hopefully for the team to succeed, it will be. So to answer your question, the series of projects which kind of are listed out there, I'll just go through kind of, this was the last offering of this course a year ago, and I'll just go through what these particular projects did very briefly so that you can kind of get the sense of what was happening. So the first project, auto grading of circuits. So what this group did was, you know how in beginning E courses and all, you kind of hand draw circuits, okay? And the thing is, again, while auto grading kind of software has begun to emerge from a lot of software oriented classes, some of you may have encountered them where you submit your program and it's tested and all, but it's much harder to do where for things for early courses where still students hand draw stuff. So what this system was doing was it was basically taking snapshots of circuits that students had drawn, and they created a system for that. Basically, the paper slides in, they take the images, and then they essentially do some image processing slash machine learning kind of techniques on that to extract the circuit topology from that hand-drawn thing and then test it against the correct. Okay. Zombie bot. This was done by someone as a project which they were targeting as something that could be there in entertainment parks and stuff like that, kind of like a humanoid thing which you can go and punch. And it was equipped with yeah, sensors inside a soft outer exoskeleton. And then sort of there was a scoring criterion and stuff like that. Okay, but main thing really it was essentially trying to classify your punching things. So imagine this is one way of looking at it is that if you're boxing and you're practicing against those sort of bags which you sort of punch against, this is a version of that. It's a humanoid shape, and it is measuring the force of your punch and all, and giving things based upon that. Brake alert system. So the idea out here was um, that yeah, I noticed that this group went past with the title obviously all wrong, Break Alert. But in any case, what this project was about was that you're driving, and you know how DMV books and all, they always give you this guidance that how much should the separation be between you and the vehicle in front. So kind of the idea was that that separation depends upon your speed and of course the intercar and that based upon that the intercar distance. Um, so a couple of things. Number one, warning this driver itself that you are sort of too close, uncomfortably, dangerously close, but also perhaps warning the driver behind you to not tailgate too closely. So it involves measuring the distance and then using the speed information, which I think these guys were getting from that OBD2 interface, and then combining that into this system. Um, Scalable simultaneous localization and time synchronization. Actually, this ended up being a research paper published at a conference, and this was basically a bunch of wireless devices which collectively exchange information using which the nodes synchronize their time and also learn their relative location. And it involved essentially, if you're familiar with the concept of Kalman filtering, so this was essentially doing a distributed Kalman filter or like a distributed state estimation. So pretty nice piece of work, but these guys had to work quite hard. Smart prompter. This was the project which was more of a mobile phone app kind of a project, but what it was trying to do was that people who have speech impairments, they often struggle for, so this particular student sort of had it in the sense that like he would often get stuck and hunt for the next word and all, right? I mean, yeah. So the idea was that this system, making use of some natural language processing techniques, would prompt, suggest additional words as the next word, and then you can kind of select it. So that was. Carbot. Um, this was a project which was seeking to essentially create a fuel consumption aware way of routing you. So essentially, as it would suggest navigation routes, it will kind of take into account availability of gasoline along the path as well as the fuel consumption. It was motivated originally, although the project got kind of morphed, was that in an electric vehicle, figuring out the path and the actual battery consumption is much more complicated, depends upon the terrain, the overall kind of elevation gain and fall off. And there is also the complexity that, like in a gas driven car, if I want to put in 5 gallons of energy, it's going to take the same time. But in case of a battery based car, if you want to fill the battery by 20% capacity, then going from 80 to 100 is very slow, but going from, let's say, 10 to 30 is very fast. That's the nature of the battery. So it's like the emptier the tank is, I can put in the energy. Okay, so it becomes actually a complicated routing exercise. I have an electric vehicle, so kind of I ended up relating to that, but these guys then kind of transformed it into a gasoline vehicle. Capacitive touch sensing over a Swift. So what these guys were doing was they were basically designing a interface for drivers to interact with the car on the steering wheel. Okay, and one of the ways that human interaction with these systems can be done is using capacitive sensing. It's a little bit like how the touch screens operate, right? So when you touch it, it's really sensing some change in capacitance. But one of the more advanced ways you can do it is to sweep over the frequencies. So essentially, you sweep over a band of AC frequency and then look at the response there. So these guys essentially design a system for drivers to convey different kind of gestures on the steering wheel using this kind of capacitive system. So that's what was happening there. Um, Boarding assistance system is actually bus boarding assistance system. So this was uh, a couple of students who kind of went after creating a aid for visually impaired, and the specific problem that they were decided to address was that when blind people who normally go around with a white cane, but it kind of is tricky for them to navigate through, like a bus comes and they have to board and they have to sort of identify where the door is. So what this thing was doing was, it was a smart cane of sorts which had some sensors and all, and it would basically try to identify the door opening, so kind of guide them through. There's a fair bit of effort in devices which assist against various kind of human disabilities, and it's a rich area for project ideas. Um, are you working out correctly? This actually also became a paper, and this had to do with um, workouts in gyms where you work with free weights or kind of the weight machines. And the problem is oftentimes you do it incorrectly, right? Too fast, incorrect motion and all. So what these students did was they used, I forget the name, what these sensors that you buy, a company sells, which basically look at the surface electrical activity, and from that they kind of you can make inferences about sort of how you are using the muscles and stuff like that. So combination of sensing and machine learning, and one of the student who was doing it, he's a kind of um, bit of a health geek, so he kind of enjoyed doing it quite a bit. Um, Smart home. This was basically uh, seeing whether we can learn. So sensors at home, but the idea is that uh, could we begin to learn about activities of the occupants and all without having to train them there. So one of the problem in smart home kind of settings and all is that every home differs. And a lot of machine learning techniques, the models they use depend upon so-called supervised learning, which is you train it for a particular sensor, for a particular type of scenario. So this was an attempt in kind of creating something which was more, which kind of self-learned. So the idea was that self-learns with minimal supervision, basically, okay, or in a new deployment. So the kind of idea is we kind of deploy these things, and then for a while, using information from the phone. So you kind of sacrifice privacy in the initial phases where the system learns about you. Are you at home? Are you not? These kind of things. And then figures out which sensors predict that. Okay, so you kind of go through this phase where the system adapts to your deployment. So that's what these guys were doing. Big success, complicated project. Cyclops programming language and compiler. This was actually a one-person project, but turned out to be quite good. So the student became then my master student, did this project further, became a paper recently. And this was basically creating a simple programming language plus a compiler associated with it to let you program real-time units which are available on certain processors. So certain processors have a main processor, and then they have so-called PRUs, or programmable real-time units, which are essentially very low-level microcontrollers. Okay, so kind of idea is that you can have your Linux system, but then if you're able to make use of the specialized hardware, you can also have like nanosecond level control on the pins. but they are a real pain to program in. So what this student did was to essentially create a very nice sort of programming language system around that to just and the runtime environment and how you deal with it. During his subsequent work, obviously it led to the paper and all. There was a bunch of other stuff that he ends up collaborating with my student, but that was this thing was a project. So on these ones, I have given the URLs. I have a bunch of other from the preceding ones where I have not listed the URLs, but I'm going to try to collect them. But at least there are names, but I'll try to kind of collate them. The problem, as I mentioned, that has happened is many of these things, because I did not insist on project website in any singular place, so they're kind of all over the map, and many of them have disappeared since these students, I mean, you see that goes back to 2008. So companies die where these websites were hosted. So I'm hoping that the GitHub approach will give a bit more longevity. Questions on the project? Okay. Uh, uh, you already know Piazza, but if you haven't, sign up for it. On Piazza, you can set things up so that you either get an immediate mail, an hourly mail, or a daily mail. If when I send something out, if I view something as particularly urgent, I push it out immediately, irrespective of your settings. Make sure to use an email address which is trustworthy. Historically, I've always had problems with students who had Hotmail addresses, and also if you're using your addresses from countries such as China, which aggressively block email addresses. So again, maybe use some safe address there. Okay, but point is something that you just should figure it out. I will make announcements on Piazza only. Occasionally, there might be things which are password protected, in which case they would be as shown out there. Um, and on the Piazza, the link is there. But basically, as you notice, I tried to record the lectures uh, as well. So um, I it requires a conversion step, which takes as long as the lecture. I usually get lazy, and therefore it takes a few days for me to put it up out there. But there's a YouTube channel where you will find it. I seem to have some problems when I was trying to set it up. Usually it shows 3, 2, 1, but it didn't. So maybe it's not getting captured today. Um, but again, this is not a promise. You shouldn't rely on it. It's not if you decide to skip a lecture and I fail to record it, not my problem. Um, the coursework will need some hardware platforms, and very generically, a lot of these systems that we work with, there's sort of three components to them. There is kind of like this tiny little embedded device, okay, often sort of a simpler microcontroller running some specialized OS, or perhaps no OS. Then some sort of a, loosely speaking, a gateway class device, which may have sensors and all also, but typically it's something like capable of running Linux type thing or Android or something like that. Could be a smartphone, could be some single board Linux computer. And then finally, things running on the cloud. Increasingly, lots of services have emerged out here. Microsoft and Amazon on their data center services have Azure IoT and AWS IoTs, and there are a whole bunch of other companies which have begun to offer things there. So there's a rich milieu of stuff out there. So for embedded devices, when we're handing out an early homework, just for it's going to have very low credit. It's super simple, but if you find it hard, then that means you are in for trouble in this course. So just treat it that way. It's basically going to be generating some simple waveforms, okay? And I want you to see that do you know how to use timers and these kind of resources, as opposed to writing it very simplistically, which leads to timing problems and all. So just think of it as a self-test. It will also be a way for you to familiarize. In any case, the platform that we'll use on the embedded edge is this particular platform, UCLA 144, blah, 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 blah. It belongs to something called Mbed, which is an operating system that ARM supports. And the nice thing is that it has a cloud-based IDE for development as well as something which you can do it locally. It's super simple to use and yet lets you do bare metal programming or if you want to run the OS. So I kind of like it. I've been using it for a number of years. We use it in our research also very heavily, and I convinced a lot of my colleagues here to use it. So it's pretty well done platform. And this particular board, there's a whole bunch of boards which support embed. This particular board is a reasonably good one with a fairly recent M7 type processor, bunch of analog digital IOs and also a pretty capable board. It sells, I've noticed, anywhere from 23 bucks plus shipping and tax to some stores which try to fleece you on Amazon where prices are like 40 bucks. Anyway, you have two options. You can buy it yourself or you can borrow it from me. But unfortunately, after some experiences in the previous courses where students would drop and then even threats and all won't work, and so the model here would be that if you check out, you have to give me a $25 deposit. My price for the bulk purchase, I think we did it from Mauser, was $23, and there was couple of dollars of taxes at 10%, and there was shipping. I'm not going to worry about that. But the point is, I wanted to return the thing. Okay. So you are always welcome to do it, but it's not required. You can just buy it yourself. Do it if you plan to stay in the course. Do it today. If you plan, I have sufficient to support a class of 30 if everyone decides to borrow from us. Okay, and you will give your deposit in cash. I'll give you a receipt. You return, you get that money back. Okay, that's how it's going to work. Any questions about this?
So this is going to be used for the homework?
Yes, and it's also a good piece of hardware for projects. Yeah. It's unless your project excludes kind of the low-end microcontroller entirely. Okay. Likewise, for the gateway platform, I'm still kind of toying between various options. We love to use BeagleBone, and I most likely stick with that. Last time I tried the experiment of letting students pick their own, and it kind of became a bit complicated. The only problem with BeagleBone is that it is more expensive than Raspberry Pi, which sells for about 30-35 bucks, whereas BeagleBone, at least the version that we kind of like to use, is almost twice the price. But my hope is by that time the class would have settled and I can trust you guys and hand that board to you without worrying about it. Okay, so we'll see how it goes, but generally speaking, so there's certain nice things about BeagleBone which include, among other things, it has analog output, analog, full-blown analog I/O capabilities, which Raspberry Pi doesn't, without adding additional stuff and all. Raspberry Pi's nice thing is a bigger community and much faster processor. BeagleBone also has the PRUs I was talking about, which give you that real-time support. So there are trade-offs, and there are obviously a bunch of other boards which are out there. We can kind of, but you don't need it immediately, so we'll decide. Cheating and plagiarism. So given the nature of this course, programming homeworks, no exam, so I don't have any setting where you just sit inside the room and all. So I'm going to be, I have no choice but to trust you, but then you have to reciprocate that. The usual sort of consequences apply of any honor code violation. But the main thing is that, number one, if you make use of any one other than your own input, then firstly check with me if it is okay, and secondly make sure to cite it, okay, because the problem usually comes when you hide this part. Just remember, university can turn back your grade retroactively also. So just because I don't detect it during the quarter doesn't make you scot-free. Subsequent detection also kind of applies. I certainly encourage you to discuss what a homework might mean and all. Do it on Piazza so that everyone gets to know, but your work should be your own. Final bit, there is some impact of travel that I have, which I'll try to handle in a variety of ways. But basically, as of now, it seems like there are 2 Mondays and a Wednesday where I would have conflict, not being able to handle this. So some of historically, there are always two or three things which in any case one of my PhD student presents, like a discussion on Android and things like that. So I'll try to have those take place in these dates, but sometimes it doesn't work out that way, in which case I'll record a lecture and then you watch on your own. Okay, any questions? Okay, so one other thing I want to do at this point is um, attendance. So the way you do it is you go to this URL and fill it out. You have until 4:30 p.m. to do it. You can just take an image of it. That's perhaps the easiest thing to do and just handle it. So I'm going to leave it around for a bit and let's take a 5-minute break and then restart on the main lecture. Okay. And by the way, I won't be doing it throughout the course. It's just for the first few lectures so that I get the sense of who's there. Say it again? I will. Yeah. So the question here is topics for the project. Hopefully towards the end of this week, or I'll open up the Google Doc slides that we are working with, and you can start looking at it. But not every project description there is in a mature state, but it will at least start giving you some idea. Okay. And if you have your own, come and talk with me. But please do so only if you are enrolled in the class. I don't want to get false hopes up and all. Okay. So.
Another question. When can we meet a project mentor? Do you assign them to us or something?
No, so usually the project page will list the project mentor and their email addresses, and I'll make sure that they do. Okay, and they're all my students, and they all sit in that 1762 Bolter Hall. Couple of my students are in this class also, so they can always guide you towards that also. But anyway, so okay. Any other question? Okay, so this next set of slides is really meant as high level sort of look into kind of issues and all which are arising in embedded systems. You saw a little bit of that in those 2-3 slides earlier on in the introductory slide set, but here we just dive a bit deeper into that. We'll continue on this on Wednesday also a bit. I won't be finishing this today. I guess there are a whole bunch of trends in sort of computing technology. Moore's law you are very familiar with, but there are equivalent things which relate to memory, network bandwidth, and stuff like that. But they all conspire together to kind of lead us to this scenario where we have a sort of periodic shift in the generation of computing or computing paradigm that we deal with. And we've gone through all of a whole bunch of these things. I think right now we are in this phase where we're dealing with these IoTs and autonomous XYZ kind of things and sensors and all of various types, and we are in the midst of that. And of course, with sort of huge implications at the societal level. And one way of thinking about this thing of this change that is happening is just the ratio of computers to people. Okay, we went from an era where it was whatever many people to a single computer. My undergrad days, we had a mainframe in a computer center, and we'll go and work there, and that was like a temple of computing, and a few hundred people, whatever. My technical institute was the size of 1,000 people. We were all sharing that. To one now where we all have multiple computers, right? I mean, and that will keep sort of changing. The other thing which is happening is that just literally the name embedded kind of implies that, which is computers don't look like computers, but rather they are hidden behind physical objects of various type, and increasingly biological objects also, like things getting implanted inside us and all. And the third thing is that embedded should not suggest to you by any means that these are just small things. Okay, while it is certainly true that a lot of embedded systems around us are small, but these really come at variety of scales and shapes and sizes and whatnot, and even sort of big transportation systems and all are kind of all examples of embedded systems in that regard. I guess my my foray into kind of this discipline early on during my career at UCLA kind of started from a discipline that was emerging around that time. This is late 90s, early 2000s, something called wireless sensor network. And it was a very kind of hot thing in CS and E and a lot of engineering at the time, and sort of laid the foundation of a lot of what we see around. And this was this vision that because of ability to pack computing, communication, and sensing into kind of small devices, we can have this world where sensing is everywhere, and these sensors measure things about the physical world, reach some local decisions, communicate them, and then at some higher level, you kind of aggregate them and make some more interesting inferences about the space you are in. I guess to some level, these kind of ideas were anticipated before also. There's a very closely related field called ubiquitous computing or pervasive computing, and a lot of work at places like Xerox PARC in late 80s kind of focused on that. But the technology wasn't there. But towards the 90s and early 2000s, technology began to emerge where you could literally have low-end platforms which are very affordable and all. And in fact, a lot of the early work in this space happened here at UCLA. Professor Bill Kaiser, Greg Potty, some of these people who were very active in that, pushed the technology quite a bit. The most famous platform which emerged out of sort of this era was something called Moat, or Berkeley, UC Berkeley sort of created that. So it's a tiny little 8-bit microcontroller, short-range radio, bunch of sensors, and kind of headed towards this dream which people often called as a smart dust, but kind of lots of sensors monitoring our environment, forming a network in an ad hoc manner, talking in a peer-to-peer manner. So all of that collectively kind of went into this wireless sensor network kind of thing. Then what happened was internet happened, as an internet became a lot more sort of lot more accepted in the society. So things began to connect at, in a sense, at a planetary scale. And basically, again, in the 90s, the other big trend which happened was your smartphone kind of devices, right? Which brought with them the benefit of scale. So suddenly, sort of, we began to see lots of connectivity, as well as even more so than those modes kind of things and all. We began to see devices which were now being made at the scale of hundreds of millions, and therefore sort of got the benefit of significant more volume. So I think what we see now is really kind of a confluence of a bunch of these trends which happened. So smartphone, as I said, is one of the interesting thing is that when smartphones first came out, they had sensors, but they were not meant to sense anything about us or about the world, but their purpose was often more as a user interface thing. So, for example, while iPhone popularized the use of accelerometer on the phone to reorient the screen, but they were not the first. There were a couple of other phones with that capability, but the point was accelerometer got put into the phone purely as a user interface device. I rotate the phone and the screen changed orientation. Likewise, there was a light sensor, but the purpose of light sensor was power management. I pick the phone, it comes close to my cheek, would discover that there is darkness, and therefore turn off the display. And so it was being used as a proximity sensor, and so on and so forth. So what changed, what happened though, is people soon realized that these sensors can be used much like we were using those modes and all for, which is to sense people, sense things around us. And so that's one thing. The other thing is on the cloud services, the internet, what that made possible is connection to data centers and with powerful computing. So suddenly you can begin to process sensor data and do control actions in ways that you previously couldn't. So I guess the story, so while the story for the first 10 years or so of sensor networks was tiny sensors, ad hoc networks and all, but sort of since then it kind of forked, and a parallel story emerged, which is these phones and devices connected to the phone became another category of sensing devices, which are mobile. They are with us, so we don't embed our phone into our buildings and all. But the nice thing is they are with us wherever we are. So now, oftentimes when you need to sense something, you oftentimes have a couple of different ways of approaching it. You can say the human agent has a phone and I could make use of that, or alternatively, the space the human agent is in has these sensors embedded in them and I can make use of that. And they both have kind of pros and cons. Um, Phones we carry, but if you suddenly start expecting that I'm going to have a whole bunch of other sensors, then it becomes painful. So, for example, let's say you want to monitor someone's health condition. There are a whole bunch of different sensors, even things like ECG and sort of wrist-based things and whatnot. At some stage, they become too much. Also, like I mean, trying to wear that chest belt is one thing; doing it during exercise is another thing; doing it 24/7. So there's always been this tension between sensing right at the object and sensing more remotely. And that sensing from the ambient or sensing from your wearables, and I think that continues to play out. Having said that, smartphone clearly captures so many interesting things about us because so many things for which there is no sensor, it manifests. They manifest as our behaviors, and smartphone captures our behaviors. Okay, even little things like how we type, how we speak, all these kind of things is continually collecting has data about that, and therefore it became. I think a lot of research over the past 10 years has really been towards that. To the extent that at this stage you have things like people detecting mental diseases, this kind of stuff using the data from the phone, things for which there are no sensors. So whole bunch of stuff out there, whole bunch of cloud services. I gave some example of some of the more third party kind of stuff, but generally speaking, they started out with services which were simply about storing time series data to now where they have mated them with not just storage and database and querying, but the ability to do some powerful analytics using the machine learning kind of algorithms and all. One other thing which I think is currently undergoing is the following: um, deep learning. How many of you have heard of deep learning? Okay, so wow. So how does it differ from standard machine learning? Anyone? So I could use decision trees and support vector machines and linear classifiers and all, right. So there's a whole bunch of stuff classically have always existed. Uh, Deep learning use neural networks, right? So, but what changes? Hmm? Number of layers. I mean, I guess there is not much of a concept layer in many of those other techniques. So, barring some special cases. So, I'm looking for like, I mean, uh, besides the fact that I guess deep learning stuff is doing very well at some of the tasks like speech recognition and image recognition and those kind of things where standard approaches kind of maxed out. Um, One thing which has certainly changed quite a bit is the amount of data you need to train these things. So these number of layers, but more importantly, these are some of these networks have humongous number of layers, and you need enormous amount of level data to do it. But if you have that, then you win big. And fortunately, with the smartphones and all, you have abundant amount of data. Unfortunately, it's not always labeled, so you cannot necessarily always make effective use of it. But if but there is plenty of data. The other thing is one of the hard problem always has been is so-called feature engineering, which is what feature should I use to feed into my classifier? Okay, and that often tends to be kind of a bit of a black magic. And one of the things about deep learning type systems is that the lower layers of neural networks, they kind of learn the best features for your signal for that task. It's a view that is often refers to as or they're auto encoders. That is, they kind of learn how to best encode the signal for your particular task. So what has begun to happen now is that as the ability to as the availability of data has increased, and as availability of computing has increased, suddenly your ability to make interesting inferences is getting a lot easier, because you don't need to be as much of an expert, the come up with the features and all. And that the second thing is these systems are doing much better. Uh, very in a lot of things, like there's a paper a few weeks ago that I was reading, where this was out of NVIDIA, and what they were trying to do was they were trying to learn how should a car, autonomously driven car, react based upon what it is seeing in front in terms of roads, so like obstacles, and whether on the lane, how where you're situated and stuff like that. And classically, we would have approached it in a very trying to understand the physics of the problem, right? We'll analyze the image, we'll look for the objects, sort of work of that. What these guys did was something incredibly simplistic, but beat the existing systems. What they did was they basically equipped a whole bunch of cars with humans were driving, and they put the sensors to get the labels. So they basically saw how the humans were reacting to different conditions. So they had a corpus of images and the human reaction to that. And then they trained a neural network using that, and it beat any other system that previously existed. So the point is, if you can structure your problem so that you have data, label data, and then suddenly sort of can create complicated inferences without kind of going through the tortuous pathway that historically had been done, and of course much more simplistically previously. Okay, even things like activity recognition, trying to detect walking and all, you would see a kind of a lot of literature where trying to parse into the structure of the signal related to the physics of the phenomenon. I think in many domains after domains, we are seeing that all of that can be short circuited. So some interesting sort of things happening, and cloud services are playing a big role there, because learning for these deep networks, and even oftentimes even doing inferences and all, it's fairly compute intensive. So not quite, learning certainly is not yet at a level where you can do it on the edge devices, on the embedded devices, and therefore cloud services are playing a big role out there. Okay, so what we therefore have is okay, too many animations, but kind of a bunch of these different technologies which have together kind of come together to create this IoT, CPS, these kind of things. Okay, I'm going to skip a whole bunch of slides, whose main point is that there's a lot of interest and also a lot of belief that these things may just be hype. So let's see, yeah, okay. So sort of just if you were to go by where venture funding is going and stuff like that, or courses like focused on IoT and those kind of things, and obviously a lot of interest, but there are also sort of people pointing out that just like AI, we have often gone through these phases where people talked about embedded devices, network connected together, and then there was a winter, and things would die and then again start. So the vision of smart homes and all has existed, okay, from 70s and 80s, but lots and lots of struggles, and everyone thinks that this time is going to be different, just like we think AI this time around is different. Maybe not. Time will tell. But certainly, a bunch of different technologies have come together at this point where there is at least a qualitative difference from sort of previous attempts, and hopefully things would come out to be better. So at this stage, what we have is a whole bunch of these technologies which come together, and to properly understand and frankly to design and build these kind of systems, you really need to be a bit of a jack of all trades. Okay, you need to know about kind of what's happening in these edge devices. You need to know about what's happening in these middle tier of devices, the network, and certainly how you can make use of the insane amount of computing that data centers provide. IoT examples, a whole bunch of them that exist. And if you go to Amazon, they have a whole section of their website where sort of automation related products are sold, and there are just way too many of these products. Okay, I've just kind of listed a few of these, but there are lots and lots of more. Um, so certainly an exciting uh, sort of space in terms of commercial activity and all that's happening around it. Um, the this view of I guess encompassing view around this thing is that we are really creating these systems where we have sensors, actuators, decision making, perhaps multiple loops of decision making happening, and they are all coming together into kind of this human cyber physical system kind of thing. One application domain which I have been interested in over the years is mobile health systems, where sensing personal health and then based upon that nudging people's behavior or intervening medically to achieve certain health goals. Okay, so it could be someone is a I don't know, congestive heart failure patient and their exercise regimen or sodium intake and these kind of things affect them. But you've got to be able to sense them so that you can intervene because the conventional paradigm is that when they go and see a doctor or when something dramatically bad happens and call emergency. So this continual healthcare and continual guidance and coaching is something that lots of people are interested in and are working towards. And part of that story also is developing the interventions themselves. So medical science is also interested towards it. One of the very large scale effort in the world which is happening is right here in US where National Institutes of Health last year started a $250 million large program where started with that. It's going to be a lot bigger, but what they're doing is they're selecting a cohort of 1 million people um, who will, with wearable sensors and mobile phones, they will track their health data over a course of a decade or so. And kind of the idea is to help develop interventions that previously just couldn't because we just didn't even have the data to begin with. And lots of people. Professor Kaiser's group out here is perhaps the most prominent one here at UCLA or Maria Surabrade in CS, but immense amount of activity in this space happening. And for a lot of things I mean, it's what for things like blood pressure and your heart waveform and all, they're easy. On the other hand, things like is someone depressed or is someone fatigued, and these are much more complicated. But nevertheless, by fusing information from a variety of sensors, you can kind of make headway there, and then close the loop, intervene. Okay, and that's kind of the holy grail in these systems. Another area where a lot of work like this is happening is towards sustainability, buildings, um, affecting people's behavior so that they make use of building systems and other systems which are coupled with building systems more efficiently. So energy saving, water saving, stuff like that. Again, these are sort of control loops where human agents are an integral part of it. Um, Today's ECE seminar kind of went over some other examples of this nature. One way of looking at it is really that rapidly our world is becoming one where we have variety of these kind of devices, swarms, as many people like to refer to them. So whether they be drones or vehicles or stuff in smart buildings and so on and so forth, and collectively, like each one of these is part of an application where you really have this sort of perceive the state of the world, then use some AI type techniques or control theory type techniques in order to figure out what's going on, and then finally take some action on it. And a question which also comes up is that what would be the best way of organizing these things? What will happen? Right now, a lot of these systems are one-off. They are being done separately and all. But a lot of people in computer science have now begun to think about that how will we systematically support these classes of applications. So just like the internet became terrific for communication and information access and all, if you were to scale it to these kind of applications, what needs to be done? What's the networking slash distributed computing infrastructure look like? One question which comes up early on there is that all of this, would it be done in a manner which is purely distributed? This is a little bit like the early days of sensor networks where sensors just talking to each other. So you can imagine, let's say there are people often envision there will be all these drones and drone-like devices. Maybe they'll just handle themselves. They'll just talk with each other in a purely distributed manner. Or, and possibly more likely, we may end up with a situation where perhaps low levels of control, kind of like our reflex actions, are done within the devices, but then there are some higher tier loops, more like the planning and all, which will happen through some sort of mediation by cloud services. Okay, so what an individual traffic light is doing may be driven by the sensors at that intersection, but what is happening at the city scale and all is probably being set up by what the city scale traffic sort of something within the global view of it. So, so this is barring sort of certain things like military settings and all where there might be isolated deployments. Quite likely, this is the viewpoint that would emerge, and indeed, such is the case. That we are creating these kind of systems. The problem is we are creating these things all sort of standalone. So in recent 1 or 2 years, what we are beginning to see is some projects which have begun to emerge, which are saying, that, okay, let's step back. Could we create an infrastructure which can, where a lot of these kind of things can coexist? Kind of the term which is often used as multi-tenancy. That is just like internet supports a whole bunch of applications. Could we create a networking slash cloud services infrastructure which supports a whole bunch of these? So, for example, there's a project at Stanford called Big Control, and what it is doing is basically saying that look, we are going to have a whole bunch of these different types of swarms, different kind of devices, but let's create the networking and the data center infrastructure which can support all of them and kind of factor those necessary capabilities as services that we need to provide. So just like on internet we saw things like web services and all emerge because there was a common need for it. So likewise, when we look at these sort of perception, cognition, action type applications, what would it look like? What are the kind of things that we could do, and what are the things, interesting things we could do which we couldn't do without? So, for example, if I have lots of computing, then the way you approach control can begin to change. If I was doing control only at these devices, then I don't have access to historical data because I have tiny amount of memory. I cannot do complicated computation. Whereas if I'm doing stuff out here, I have historical data. I can do simulations. I can do what if scenarios of how the world will evolve, making use of GPUs and FPGAs and whatnot, and do sort of fancy model-based controls and all, which one couldn't do otherwise. So that's the opportunity. The challenge is that if you're doing all of this kind of stuff, then suddenly you have to deal with both kind of a pretty messy organization of computing out here. Another thing is you're into this world where latency to these networks and all becomes an issue. That suddenly you have to start making sure that your decision-making loops, which are running across data centers with their virtual machines and all, are still able to meet timing requirements. So a whole bunch of activities happening. There are sort of Stanford has this project. There is a new project that I'm part of, which is going to start in coming months. A project called Connex. If you go to connex.io, it's a CMU-led project, and so we are part of it also. So what you see now happening is that this collection of technologies are moving towards, I guess, their eventual thing, a Skynet controlling everything. Okay, no one. So Skynet, anyone knows what it is? No, you do. Okay, cool. Okay, I thought maybe I'm too old, so that's fine. Okay, but I am. But yeah. So anyway, so I think we are kind of getting closer to this thing where instead of just sense to now sense and control and kind of do it over this sort of worldwide infrastructure. Um, let's see. I already talked about that how architectural way that has emerged, a way of thinking about, at least in the IoT side of things, as this device gateway cloud or embedded gateway cloud kind of structuring of this, where you have this tier where you have either stuff born or implanted or embedded. Then you have things which in the middle where it could be your home gateway or your smartphone, which kind of in part is a computing and sensing device on its own right, but it also provides the long distance connectivity back to the internet, which those tiny devices don't on their own have. But it's always fluid. I mean, I have my new Apple Watch and this has a cellular radio on it. Okay, so it's not quite here either in the sense some of these things begin to evolve with technology, but nevertheless, there is certainly kind of a distinct uh, sort of capability point that kind of exists between these two layers. And then you have the cloud services. Actually, another interesting thing which is happening, which I didn't mention, this internet here in the middle. There's a new technology which is gaining rapid sort of adoption is something called software defined networks. Anyone heard of it? What does it mean?
You don't specifically specify another topology, but
Mhm.
the nodes themselves sort of created, distributed network.
Okay. Okay. So that's certainly one aspect of it. More broadly, what it is saying is that the network infrastructure, the routers and the switches and all, instead of being fixed function devices, are now programmable. Okay. And in fact, you could say that switches and routers were an example of embedded devices which were truly single function. Um, uh, what uh, what started so it started out with sort of what you're saying, the topology is doesn't need to be fixed and all, but increasingly we are also seeing that other things could be done while my packet is going through the switch. Perhaps I can do some processing on it and all. There are programming languages. There's a programming language called P4 which has emerged to program that network. So even computing doesn't have to be at the data center. Right now, we are stuck with computing is either in the data centers or is in these devices. But we are headed towards a world where computing could be sitting all along. Um, if you think about it, networks started out as being data transport pipes, right? That's our view of network is. But actually, that changed some years ago, whatever, 10, 15 years ago, when companies like Akamai and all emerged, it began to cache information. So when you access a web page, it doesn't necessarily mean you're going to that machine. You may be actually going to a server, a storage cache, which is sitting at Time Warner, let's say, if you are a Time Warner customer. So the network already has other stuff which helps the application, transcoding of media, a whole bunch of other stuff. And I think that trend is pushing forward. Now, the reason it is relevant for our discussion is I mentioned that latency as we move towards control is going to be important. And one of the ways you could begin to address latency is that instead of saying, my choice is not necessarily to go all the way out here, maybe somewhere in the middle, I could do better. So these are the kind of things which are happening on the research side. And in each one of these layers, there is a set of technologies which are playing their roles. Okay, um, on the embedded side, certainly a lot of stuff has happened because of the way processors have advanced. Okay, and there are a lot of interesting things happening. Firstly, sort of just in the span of my roughly 20 years or so working in this space at UCLA, I've seen from going from where people said, it will be just 8-bit microcontrollers to now Apple Watch is a 64-bit processor. Okay, so we've sort of moved within 20 years from kind of very simple to sort of some the kind of processors, at least in some senses, are similar to what exists out there. I was also kind of uh, the new iPhones, for example, the processors there are more capable than the processor in many of the Apple laptops of the current generation. So that boundary is being blurred in many significant ways. Memory technology has advanced quite significantly. It used to be that assumption you could safely make in computing was that if you need persistence, that is, the data remains there while the power is turned off, then your only choice was to go to sort of disk drives or slow flash drives. That has changed. Now we are seeing new kind of memories which are as fast as main memory but are persistent. So kind of different. Uh, so they are all impacting how we approach things. The trade-offs between computing and communication and all. Another mantra which I grew up with early on, and we wrote tons of papers and all, and that said that computing is cheaper than communication. Okay, so you would hear, including, for example, in Professor Potty's textbook, in the space, it says, oh, cost of sending 1 bit is 1,000 times the cost of processing 1 bit. Okay, and that was all true. But then emerged these radios which work by so-called backscatter technology, where the energy to transmit doesn't come from the radio, but they hog it from TV stations or Wi-Fi. So suddenly, cost of communication plummeted. And now we are in this regime where cost of processing a bit in certain kind of systems is many times, many order of magnitude more than the cost of sending a bit. So lots of things. So the other thing to keep in mind is that if you work in this space, it's important to have a pulse of technology trends because that is how you are going to exploit them and create new architectures. So very important to sort of understand that. This gateway is a source of problems. I mean, the world would be really nice and convenient if we only had that first layer, right? Sensors or actuators directly talking to the cloud and just do it. The problem is that yeah, given the way the technology is, we often don't have a choice. We can't really pack these tiny devices with too much, or at least certainly not with some sacrifices, okay, cost or battery life and whatnot. So gateway introduces vulnerabilities. It's a point in the middle which its own security implications, but we often kind of see that. Okay. Um, yeah, I'm going to. This is an example of system at Berkeley, kind of making the point that how you see what's happening in the car. So car is a great example of how multitude of these technologies are coming into play. So many modern cars, most modern cars now have some independent connection back to some cloud services. At the very least, they get some sort of navigation data and all. But in cars like Tesla and all, they do also fleet-wide learning and stuff like that. The phone that you have in the car hooks up to the car and provides its own independent way. So ways and all operate on that. So there are multiple pathways that exist into some of these systems. This is some work out of Berkeley where they kind of created a device and which kind of lets you create a control loop like that. And another enabler really has the processing technologies. Processors in a variety of ways. I kind of mentioned that 64-bit in these tiny devices is something that is happening now. But more generally, lots of action happening. I think one of the most exciting thing which has happened is that software was considerably revolutionized by open source, but hardware always remained closed source, okay, because you were dependent upon the Intel or the ARM and all. There is this processor called RISC-V, which came out of Berkeley, which is an open source hardware, open source processor. So now suddenly, now you can create not just open source software, but your entirety of your system, right down to the chip or stuff running on the FPGA is all open source. You can modify the processor, you can add new instructions, and that's creating a lot of excitement and a lot of interesting ideas that are sort of happening in the result. So I'm at past the scheduled time, so I'm going to stop out here and finish this thing off on Wednesday and then move on to the first lecture. So meanwhile, again, my request, if you decide to drop the class, please officially do so as well so that I can hand out activities.